Okay, we should get started. We're right on time. Is everything okay online? Can you hear me? All good? Okay. And the live stream is working? Okay. Let me. That's good. The camera looks okay. Yeah, I don't know. Just don't touch it. That's always a good idea. Okay, let me close the door. Okay. Because we have fewer and fewer people. Holidays? Well, approaching. There's approximate holiday computation. I thought holidays didn't start yet, but yes. I guess if you're in the US, Thanksgiving passed, so. Okay, well, we don't have a lot of lectures left. Today we're going to cover interconnects, and tomorrow also. And then next week you have an exam. Hopefully you guys are not stressed about it. We have past exams available. And the last lecture next Friday will be a special lecture on special topics, which you will see at that time. So we have only real 2 lectures left. Well, 2 plus 1 after the exam. After the exam lecture will be fun too, so I'll recommend attending it or watching it. Okay, so today we're going to cover interconnects, but before we jump into it, I have an announcement. If people are interested in computer architecture, we're having kind of a reunion of our group, Sapphire Research Group, next Monday, December 15. You can see that date over here. And we'll have a first conference, which brings together some recent PhD graduates as well as postdocs from the group. And they are at different places, as you can see, except for Geraldo, who's going to join a different place soon. Geraldo is the most recent graduate, if you don't count Rahul, who's not here right now. But basically, we'll have 13 talks, and 11 of the folks are going to be flying in or coming in from different places. So this is a good opportunity to interact with some of the recent graduates who've done top-notch work. 2 of them are coming from the US, actually, specifically for this conference. So it's going to be a full-day event on Monday. It's going to be live streamed online. It's also going to be in 2 different rooms, morning half and then the afternoon half. And you can find the program online linked from YouTube. So if you're interested, that'd be great. This is actually something that we wanted to do for a while. We have now 25 PhD graduates and almost 20 postdoc graduates. That's about 45 people. And getting back 13 of them is actually not that bad, you know. I didn't invite everyone because otherwise it'd be a nightmare to schedule the conference. It'd be 3 days as opposed to 1 day. Even fitting everything into 1 day is good. And this is also a good opportunity to interact with people who have chosen different career paths after their PhDs or postdocs. Some of them are actually in academia, as you can see. Some of them are in industry, and some of them are going to talk about what they're doing in industry or academia. So it's a good opportunity for discussion. Then we'll have some food available at the conference. So anyone is welcome to attend. If you're attending on YouTube, you'll forego the food, of course. Okay, so with that, let's get started. Essentially, we've covered a lot of multiprocessing in the last several lectures. We talked about multiprocessing, fair comparisons, Amdahl's law, which is really important in anything we do, actually, not just multiprocessing. We talked about important issues like memory ordering, memory consistency, cache coherence. We discussed how these things actually impact both programmability, ease of programmability, ease of debugging, and also performance at the same time. And we discussed especially the performance correctness. I don't want to necessarily call it a trade-off, but a danger, let's say. Always, whenever you want to improve performance, there's a correctness issue that you may need to deal with. So today, we're going to actually talk about what actually enables these multiprocessors to scale or work in the end. So these are, just for you to recall, we discussed 2 cache coherence methods, Snoopy bus and directory. I will not go over them again in detail. Directory is much more scalable, as we have discussed, but you can actually have a combination of both methods. and we discussed trade-offs related to that. So today we're going to talk about the substrate that enables essentially all of that communication. Because if you think about it, some shared memory multiprocessing is about communication, right? You're doing loads and stores to a shared memory substrate. The memory is shared from a programmer's perspective, but physically the memory may be distributed, as we have discussed in the cache coherence lectures. And you need to enable access to that distributed shared memory. And if you really want to scale the system, you want that distributed shared memory to be many processors, right? So how do you design a scalable system that enables this? So we also discussed, for example, when we discussed directories as scalable as the interconnect and the directory storage. So today we're going to talk about the interconnect. These are some readings. We'll cover some of these tomorrow, actually, but we will cover some of these today also. Some of these are relatively old, as you can see, from 1970s as well. We're going to see the evolution of interconnection network architectures and supercomputers, and also on chip networks more recently. In the end, if you want to design a very scalable system, you cannot fit it in a single chip. You need to have some sort of interconnection strategy within a single chip, but also outside the chip as well. And today we're building very large scale systems like data centers, AI accelerators, and we're going to see examples of the types of interconnects that are employed in some of those. But let's start with the basics first. I will throw you some terminology, unfortunately. This is an area which is a little bit terminology heavy. I don't necessarily like it, so I'll try to minimize the jargon. In general, it's always good to minimize the jargon when you go into an area, because jargon adds overhead. But essentially, the key reason why we have an interconnect is to connect and communicate between components, right? And this connection and communication can be done between processors and processors. Processors can communicate with each other. One can send another a message, for example, in message passing we have discussed. It could be done between processors and memories, between different banks. It could be done between processors and caches. It could be done between caches and caches, as we have discussed in cache coherence protocols, for example. It could be done between I/O devices, and it could be done between any of the combinations of the above, right? So interconnection network kind of looks like this in a scalable system. And this is a picture from a very nice paper that we're going to talk about, which introduced the, well, okay, I guess I need to do that. Okay, which introduced message passing machines, and it looks at the differences between message passing and also shared memory communication. If you look at this over here, you have processors and storage modules that are memories. And there's a switching network, interconnection network, essentially, that connects the processors to memories, and the memories to processors also, of course, backwards. This is another way of looking at the interconnection network from a message passing, a little bit more message passing perspective. You have a processor and you have a memory associated with it. And each of the nodes is processor and memory associated with it. And then you connect those nodes to each other, right? Again, as you have discussed in earlier lectures, you can build a shared memory substrate on something like this by adding coherence, for example, or you can build message passing on top of this also. So in general, programming model and the hardware can be mixed and matched. But if you read this paper, it argues that this is a more message passing type of machine. And we're going to see this paper later on because it introduces Cosmic Cube, which is a way of designing the topology of a scalable interconnect message passing machine. Okay, so that's one example. We'll see more. So why is interconnect important? Essentially, this boils down to what we've discussed in parallel computing. It affects how you wire these components, affects scalability and the cost of the system, affects performance and efficiency, and affects reliability and security. Scalability, like how large of a system can you build? Can you actually keep adding more components? Not just processors, but think of, I wrote processors over here, but components in general. It's good to think about that. Can you do that online while the system is in operation? It affects performance and efficiency because it's the type of network that you use affects how fast can processors, caches, memory can communicate with each other, how long the latencies are to memory or latencies are between different components, cache coherence latencies, for example, and also how much energy is spent on communication. And we're going to see different types of networks that make different trade-offs related to this. And in the end, it also affects reliability and security. Can you guarantee your messages are delivered or your protocol actually works correctly in the conditions that you encounter in real systems, right? And then there's a security aspect, which is, can anyone infer message contents and communication information that you may not want to be inferred based on the communication patterns, right? So it's good to think about these. We're not going to be able to cover everything, but robustness, especially reliability, routing around faults is really important, especially today, because robustness is becoming a bigger problem. And essentially, all of the supercomputers have some mechanisms to ensure that you can still route around faulty components. Okay, so there are many parameters and goals in a network. You can see that this is actually a very nice book that is dedicated to interconnection networks. We could have a class on interconnection networks, as you can see. We could have a class on multiprocessors. We could have a class on a lot of the topics over here. But you can see that there are two different types of interconnection network systems that is very similar to the cosmic cube. And there you can see that there are many parameters over here. We're going to see some of these parameters. You can see that's reliability, availability. All of these are important. And this is the book that I would recommend, which actually covers interconnection networks in a lot of detail. We're not going to be able to do that sort of detail in 2 lectures, clearly, but we're going to try our best to cover the basics, fundamentals, and first principles. But if you want to go into more detail, it's a book from 2004, so it's a bit dated, but the fundamentals are really there. Maybe the recent examples that I'm going to give you today are not inside that book, because the recent examples are from 2025 and 2024 on AI accelerators, which were nothing in 2004, clearly, but the fundamentals are there, as you will see. Okay, so if you have taken DDCA, digital design and computer architecture, you've already seen a sort of network. It's a network, actually, not a sort of network. It was a clock distribution network. And we designed this network so that to solve a problem. And the problem was you distribute the clock signal across the processor. And because you distribute the clock signal, it arrives non-uniformly late to different parts of a chip, causing potential timing issues. So you can solve this by designing the interconnect to equalize the arrival time of the clock signal to all parts of a chip. Now, why is this important? Because as we have discussed in DDCA, you have something called clock skew. And clock skew is the amount of discrepancy across different parts of a chip on when the clock signal arrives. And clock signal is important in sequential logic because if the clock signal doesn't arrive on time, then you don't synchronize different components across the processor. And you need to basically eat away part of the cycle time for clock skew. Now, if you equalize this component, then clock skew is not necessarily a problem. So this is essentially a specialized interconnect that communicates the clock signal. And this is one example. It's an H tree type of interconnect. You can see that it's a tree, and it's H tree because it looks like H's in all of these places. And the idea is to put enough buffering and wiring such that the clock, which is generated over here, arrives to all parts of a chip at the same time, let's say. This is not an easy problem. And I think we have discussed this in DDCA. Clock skew increases sequencing overhead, meaning it reduces the amount of useful work done in a cycle. And I think we've discussed all of these right now. And these are real problems, actually. People design these clock networks. This is actually in addition to what we're going to talk about. The goal of this network is to just distribute the clock signal such that the clock arrives at the same time. And this is an example of the clock skew that was seen in the Alpha 21-264 processor in mid-1990s. And you can see that it's kind of as an H tree type of network, actually. You can infer what kind of network it has based on the skew that different nodes see. Okay, anyway, that's an important area, but it's kind of past. We used one lecture to cover this in DDCA, and if you're interested, you can take a look at the timing and verification lecture. Okay, so clock distribution network is a network, actually. Everything that we're going to describe applies to it. Now let's talk about some basic descriptions. I'm going to give you examples later, but let's define some terminology first. Every network is defined by 3 major things: topology, routing, and buffering and flow control. I put buffering and flow control together because these are actually tightly integrated. Some books separate them. In my opinion, they're very tightly integrated because buffering strategy dictates what kind of flow control can you employ, and this will become more clear. And in the end, everything about the network is determined by all of these things in combination. At the end of this lecture, we're going to look at interconnection network performance. Topology will limit your performance. Routing algorithm will limit your performance on top of the topology. And buffering and flow control will limit your performance on top of the choices that you make for topology and routing algorithm. So whenever you're designing a network, you need to consider a lot of these at the same time, actually. So topology, what does this mean? This means how do you wire things, basically? What kind of a shape does the graph of wiring look like? Specifies the way switches are wired. The best way to look at it is actually by observing what things look like the H tree, for example, right? It has an H and a tree. We'll see different types of topologies. It affects essentially everything. One thing that's really important today is building ease. How easily can you make these connections, right? Because if you actually have a lot of links, and if the links are actually wires, and if these are actually wires that you need to route by hand, for example, because you may want to connect this computer to this computer with some wires, and if you have tens of thousands of these things, and if you need to do it by hand, then you're in trouble. That's how supercomputers are actually done. That's one of the reasons why people are moving to more optical interconnects, because optical interconnects are easier to connect to each other without making mistakes, because then you don't need to wire them by hand, right? I'm going to show you some pictures, so it's good to think about this. So a routing algorithm or routing mechanism dictates how a message gets from its source to destination. And there are multiple ways of looking at it. We're going to look at both static ways of looking at it, adaptive ways of looking at it. So we're going to cover that later on. We're going to start with topology first. This is just to give you the terminology. And buffering dictates what do we store within the routers and links. Do you store entire packets, parts of a packet, 1 bit? How big is a packet? We'll define some of those. And it also, flow control dictates how do we throttle during oversubscription. What happens if your buffer is full, for example? How do you actually resolve that sort of resource contention? These are all important choices. And these are actually tightly coupled with the routing strategy also. So in the end, routing is also coupled with topology, because what kind of a routing algorithm you employ is dictated by how things are connected to each other as well, right? Some routing algorithms may not be easy because of your topology. Okay, so there's some more terminology. I'll go through this relatively quickly. A network interface is usually the module that connects the processors to the network, or endpoints to a network. It decouples computation and communication. So a network interface, the CPU is a network interface, and you connect it somewhere. You can think of it that way. Inside each chip, you have a core, and each core has a network interface. Link is a bundle of wires that carry a signal. We're going to use this link a lot. Switch, router, we're going to use these interchangeably. A switch or a router connects fixed number of input channels to a fixed number of output channels. It basically does the switching. You have some input channels or input wires, let's say input links, and you want to actually put them to the outputs. How do you do that? There's some architecture to be able to do that. And channel is a single logical connection between routers and switches. Don't worry about it if you don't get it right now. It'll become a little bit more clear. Some terminology is unfortunate, I think, but that's how it is. Okay, this is maybe easier to think about. Node is a router or switch within a network. Message is the unit of transfer for network clients. So I send a message between this processor to this memory, and I get a response message. A packet is unit of transfer for the network. So this is the network's perspective. Messages from the transferer's perspective. And FLIT is called flow control digit. This is a term introduced by that book, actually. It's actually the unit of flow control within the network. Flow control is essentially how do you handle buffer subscription, for example, buffer oversubscription, etc. It may not be done at the packet level because packet may be too large. You may store actually smaller things like FLITs. Okay, again, these will become more clear. You may divide the messages into packets and then packets into FLITs. And the FLITs may be your storage units inside the routers, okay? Okay, some more terminology before you doze off, and then we're gonna start the more interesting part. So there's also this direct versus indirect networks. Indirect networks, endpoints, meaning things that actually communicate with each other, sit inside the network. In indirect networks, they sit outside the network. So this is best seen by an example. So here you have green things. These are things that communicate with each other, nodes, I will call them. And then some other green things. These are the destinations. It could be the sources, the other way around. Essentially, the green things on the left communicate with the green things on the right. It could be processors and memory, for example. And internally, you have yellow things that are there just to route messages. Yellow things are just switches, basically. They're not endpoints. This is an indirect network because you can see that the endpoints, things that communicate, are outside the network. Inside the network, it's just switches. And this is a butterfly type of topology. If you know the FFT butterfly, fast Fourier transform, this is actually what it looks like. This is actually employed in real supercomputers in the past. So this is a router or switch. There's some more terminology, as you can see. Radix is, if you call a router has radix of n, if it has n inputs and n outputs, you can see that n is 2 over here, 2 inputs and 2 outputs. Each router is a 2x2 router. It gets 2 inputs, and it has 2 destinations. And these routers are also called two-array. Okay, some more terminology for you. So this is indirect. On the other hand, this is direct. You can see that each endpoint also has a switch next to it. And this is a mesh topology. Every node is both an endpoint and a switch. Not all meshes are like that. If you actually remove some of the greens from this, it will become indirect also, right? Some of the nodes will have the function of just switches as opposed to some nodes as well as switches. Okay? Like I think, for example, of the endpoints as processors. It's the easiest to think about it. And the yellow points as the routers. And if each thing that you see in a network has both a processor and a router, that means it's a direct network. Otherwise, it's an indirect network. Okay, and we'll see that both are actually employed in real systems. Okay, let's talk about topology. Nope. No, what happened? Okay, I'll need to share. I think it's okay, right? Use slideshow. All good? Okay, sorry. It's loading meeting. Okay. More terminology for you guys. I told you that this is a terminology heavy area, but again, this will become more clear with examples. So there are regular or irregular networks. Again, by looking at the network, you will see whether or not it's a regular graph or not, or an irregular graph. If everything looks kind of the same, it's more regular. Routing distance is the number of links or hops around the route to go from destination D or source D, source S to destination D. How many hops do you need to traverse? How many switches do you need to go through? And there's a minimal routing distance, of course, and there could be a maximal routing distance depending on the routing algorithm. And we're going to look at that. Usually when people talk about routing distance, it's the minimum routing distance between source and destination dictated by the topology. Diameter is the maximum routing distance within the network, the maximum distance between any source and any destination. And the average distance is the average number of hops across all valid routes. Of course, usually average distance is defined based on a workload or an access pattern, communication pattern. And we will see some of these things when we see papers. More terminology, you may hear bisection bandwidth. We're not going to use that much, but people still use it actually. I was looking at some of the recent AI accelerator papers. They use the term bisection bandwidth. This is often used to describe network performance. And the idea is you cut the network in half when you look at it. I'm going to show you examples of this. And sum the bandwidth of the links that you cut through. Essentially, it's the minimum number of channels spanning the two halves times the bandwidth of each channel. This is one way of approximating the network performance. This is meaningful only if topologies are actually recursive. But it doesn't account for many, many things in the network. So it's just one measure of thinking about network throughput. But it's not, certainly it doesn't necessarily correlate with execution time. So we're not going to use that as much. There's also blocking versus non-blocking. I think I promised this is the last terminology I'm going to throw at you, and we're going to have a lot more fun after this. If connecting any permutation of source and destination is possible, the network is non-blocking. Otherwise, the network is blocking. I'm going to skip the rearrangeable non-blocking. You can read the book after that. Okay, so it's good to know this terminology. I don't expect you to remember all of that or know it really, because we're going to see examples of the important things among these. We may touch upon some of these things. So as I said, we're going to start with topology. And you've already seen some topology, actually. We've talked about bus, for example, when we talked about Snoopy bus, cache coherence protocol. Essentially, it connects, you have a wire that connects all the processors or all the caches, whatever you want to connect. But topology is actually a very rich area. People keep inventing new topologies. There are point-to-point connections that are most costly. Actually, we're going to talk about that. And then there are a bunch of other topologies that we're going to cover. And there are metrics to evaluate each topology. Essentially, cost is really important. We're going to look at that. Latency is important in hops, but there's also nanoseconds. It's good to think about that. Contention is important. So we're going to look at especially these three when we think about topologies, maybe not even always. But there are many others exist that you should also think about, like energy, right? Bandwidth, overall system performance. How does the topology match the communication pattern of the workload that you're really executing on the system? So having an analysis of a system independently of the workload is not very easy, because in the end, you're going to execute some sort of workload, right? And you've seen in this class that workload is really important. So the treatment that we're going to have for topology is going to be a little bit workload agnostic to begin with, but we're going to make it also more workload oriented as things go along. Does that sound good? Okay, so let's start with bus. You already know this basically. You have, in this case, 8 nodes that are connected to a single wire or a single set of wires. All nodes are essentially connected to a single link. This is also called a link if you remember. So that's one example. This is another example over here. You have a 4 processor plus cache. You have a single bus, and they're all connected to 4 banks of memory in this particular case, or 4 partitions of memory. It doesn't need to be banks. So this is clearly simple because you have a single link, right? You cannot get simpler than this. You're not thinking about any multiple links at this point, right? It's cost effective for a small number of nodes. And it's also easy to implement coherence if you think about it, because if you do Snoopy coherence, for example, the idea of Snoopy coherence is whenever you do a write on a memory location or cache block, all of the other processors should, or caches, should see that write and invalidate their copies if it's an invalidation-based protocol. And this is very easy to satisfy if you have a shared medium, a shared single link, right? This is much harder to satisfy with the other networks that we will see. That's why people have moved to directory-based structures. Okay. Now, of course, this has a lot of downsides also. For example, if you want to scale beyond 8 nodes, 8 processors, let's say, now the bandwidth becomes limited because you have many processors hanging off a single link. There's a lot of electrical loading that happens, and the capacitance increases. And as a result, you cannot operate the bus at very high frequencies. And clearly, operating a bus at high frequencies enable you to transfer things faster, put things faster on the bus, etc. There's another issue if you actually connect a lot of things on the same link, the way we are looking at the link right now. There's a lot of contention that happens. For example, if node 0 wants to communicate only with node 1 for some reason, that communication affects some other communication, like if node 6 also wants to communicate with node 7, these two get serialized. Right? So that serialization certainly hurts performance. And you can also see the same issue over here. If processor over here wants to communicate this memory, and this processor over here wants to communicate this memory, because there's only a single link, those communications need to be serialized. Right? That's the downside of a bus, essentially. Even though these two communications have nothing to do with each other, really, the fact that there's only a single physical link serializes those otherwise parallel communications. So there are solutions to this. One solution is to really segment the bus or pipeline the bus. So now things become a little bit more tricky if you segment the bus, because you lose some of the benefits over here. Once you start segmenting the bus, maybe it starts looking at some other topology, basically, which we're going to see also. Okay, so hopefully this is clear, right? It's the simplest you can get, but beyond 8 nodes, it's not very practical. Even 8 nodes, if you want to communicate very high frequency, especially if there's a lot of communication that's going on, even 8 nodes, this is not very desirable, let's say. Okay, on the other end of the spectrum is point-to-point, where every node is connected to every other node with direct or isolated links. So in this case, you can see that node 0 is connected to every other node with direct links. So if node 0 wants to communicate with node 4, it can use this link. Okay. It can also send a message to node 5 concurrently. So there's no limitation in terms of who you can communicate with. You don't get serialized. And every node looks like this. So this is point-to-point. So this enables maximum parallelism, lowest contention, because you don't contend with anyone because you have isolated links between every single pair of nodes. And potentially this could lead to lowest latency, assuming you can make those links work nicely and short enough. And also you can lay this out. We're going to see that soon. It's really ideal if cost is not an issue, actually, if you think about it, because low latency, low contention, ignore the cost. This looks perfect, right? Unfortunately, it's highest cost because every node needs to have n connections per node, and you have n square links. So if you have 1,000 nodes, then you have a problem, clearly, right? Scaling this up is a problem. Scaling the bus up is a problem because it's too simple, and it becomes it doesn't have enough concurrency. Scaling this up, the point-to-point connections up is also a problem because of the cost, because it's even though it doesn't have the contention problem, even though you may be able to make the links fast, it's too much cost essentially. So as a result, this is also not scalable. And there's another question that I kind of mentioned earlier: how do you lay this out on a chip? It's good to think about that, right? If you have 100 of these nodes trying to communicate with each other, you need a lot of metal layers to actually make sure that you can actually lay out all of these things. I said on chip. On chip is good to think about it, but off chip also, this is a kind of a nightmare because now you have a lot of connections, n square connections, 100 square, let's say. And if someone is actually going and wiring these electrical wires across many chips, then they're in trouble, right? And if they actually make a mistake, they miswire, then your network properties are not maintained. Okay, so this is good. Given clearly buses have been employed in real chips, these point-to-point connections also have been employed, but to a smaller extent, as we will see later. So people try to actually find trade-offs in between in the end. So there's bus on one end, there's point-to-point on another extreme. Crossbar is a little bit closer to point-to-point, but a little bit more scalable. So the idea of a crossbar is every node is connected to every other with a shared link for each destination. So for example, let's assume that the blue node 0, the blue nodes are destination over here. The yellow nodes are sources. There's a shared link for blue node 0, as you can see. So if blue nodes, if yellow node 7 wants to communicate, processor 7, let's say, wants to communicate memory bank 0, it can do that while processor, let's say 6 is communicating with bank 1, while processor 5 is communicating with some other banks. So you have enough parallelism across independent destinations. But if 2 nodes want to communicate with the same destination, they need to be serialized because there's a single shared link for each destination. Hopefully that makes sense. Clearly, this reduces the overhead of point-to-point greatly. And it also makes it easier to lay out, as you can see. This is a very regular topology. I mean, this one is also regular, actually, but it's very hard to lay out. This one is actually like a mesh-like structure, which is really easy to lay out, as you can see. So basically, this enables concurrent transfers to non-conflicting destinations. The key is non-conflicting destinations, right? This enables concurrent transfer to any destination, right? Any source destination pair. So now we restricted that. And as a result, this could be cost-effective, more cost-effective than point-to-point, especially for a small number of nodes. You get low latency and high throughput, but it's still expensive compared to a bus, of course. It depends on what you compare it to, right? Compared to a bus, it's expensive. We'll see mesh. Compared to that, it may be expensive also. You still have all n square costs. You have n square connections over here because we didn't talk about what's inside this circle, right? There needs to be some sort of arbitration mechanism, some sort of buffering mechanism, depending on how you implement it. We didn't talk about flow control yet, so I'm going to give you an example of flow control. There needs to be some sort of arbitration mechanism that decides whether node 7 sends a message to 0 first or whether node 0 sends. What if all of these processors, 0 to 7, want to communicate with destination memory bank 0 at the same time? How do you arbitrate across them, right? There needs to be an arbitration mechanism. And this arbitration becomes harder as n increases. Probably you can appreciate that, right? Because you need to build an arbiter that decides that. That said, this is used in real systems. It's especially used in real systems where the number of cores and number of cache banks are limited. For example, IBM Power 5 and Sun Niagara 1 or 2, they had core to cache bank networks. I'm going to show you examples of that. So this is a crossbar design. You can see that there needs to be an arbitration mechanism. These are tri-state buffers. These are tri-state buffers with this picture. And there needs to be an arbitration mechanism that decides which tri-state buffer to enable and which others to disable when any of those nodes wants to communicate with a particular destination. So on a per destination basis, there needs to be an arbitration mechanism. And you can design this without buffers or with buffers. And these are actually choices. I'm going to show you one choice with buffers. So this is the Sun Ultra Spark T2 or Niagara T2 core to cache crossbar. You can see there are 8 cores. You can see there are 8 banks plus a non-cacheable unit. And you can see that the crossbar works both ways, meaning cores can send messages to caches, and caches or cache banks or non-cacheable unit can send messages to cores. And these are the shared links for bank 0. So this is part of the crossbar. So if I look at this slice over here with buffers are this slice. So you can see that all of the cores send their requests, and there's a 2 deep buffer over here, 2 deep queue for each requester to hold data transfer request. And you can see that there's an arbitration mechanism that consists of some sort of muxes and priority mechanism. Priority mechanism is not shown over here clearly, but you could randomly also prioritize between them. So you can see that there's some complexity involved over here. And the question is, of course, like, how do you do the 2 deep? How do you decide this to be 2 deep? And then there's a backward, for each destination, you have one of these. So there's actually an 8 to 9 crossbar in this case, because I think it's 8 to 9, yes, because there's a non-cacheable unit, which makes it 9 on the destination side. And then there's a 9 to 8 going back this way, because the banks also communicate with the cores backwards with another crossbar, or the other way of the crossbar. Okay, so the pipeline is actually not simple, as you can see. Even this arbitration mechanism is pipeline because it's at high frequency. So there's a 4-stage pipeline where each request goes through. It basically requests the destination. It goes through an arbitration. And then there's a selection cycle. And then eventually there's a transmission cycle. So you can see that there's a 4-cycle process to communicate between core to bank. And if it doesn't get selected, it could actually, if there's a conflict or contention, then it could take longer. Hopefully this makes sense, right? It's very interesting. And these are real. So this is actually Sun Ultra Spark T2. You can see that this is the core to cache crossbar. It's not small. It's almost as big as a core over here, as you can see. And the core has a lot of stuff, like L1 cache, for example, is part of the core. Okay, so this is to show you that these things are actually big. These interconnects are not small. Okay, so very quickly, I will cover this bufferless and buffered because we're going to see that later on. So how do you do the flow control in a crossbar? Meaning if multiple sources, and you can see the network interface over here, multiple sources want to communicate with the same destination, let's say the red one, you need to have a mechanism to arbitrate. And if you don't have buffers in your crossbar, there needs to be an arbitration mechanism that enables the sensing of the crossbar to make sure that nobody loads something onto the destination when the destination is being when the crossbar link is transferring something, right? So there needs to be that sort of arbitration mechanism. And this may or may not be easy to build. There needs to be some sensing mechanism, or there needs to be some other logic over here to check. Usually, it's easier to build buffered crossbars, but this comes at a cost. So if you actually have a buffer in each cross point, let's say, for example, sending from source 0 to destination 0 has a buffer, and each cross point you have a buffer. In the Sun Ultra Spark T2, it was 2 deep buffers. It could be 4 deep, 16 deep, depending on how long it takes to transfer. Now you need to manage the buffers. Buffers are good because the network interface can put something into the buffer, and then there's arbitration that happens across the buffers, which may be simpler. There still needs to be some arbitration logic. But the question becomes, how do you ensure that you don't overflow the buffers? Right? So there's some other choices that you are making over here that complicate the system. So there's no easy choice over here in the end. So buffers usually enable simpler arbitration and scheduling because you can just look at the head of the buffer, for example, in each case. It also enables efficient support for variable size packets. What if the packets actually take many cycles to transfer, for example, and variable number of cycles to transfer? But now you have buffers and you need to manage the buffers. And this is going to be a recurring theme. This is a crossbar, but you're going to see this in meshes. You're going to see this in any topology that we see. Do you want buffers or do you not want buffers? If you have buffers, how do you manage buffers? And how do you manage oversubscription? If you don't have buffers, how do you manage contention? And we're going to see very different issues depending on how we answer these questions. And this is one of the things that's fascinating, actually. Okay, any questions? Okay, basically, people have asked a lot of questions in network design because crossbars are expensive, right? If you want to build a network of 1,000 components, 1,000 by 1,000 crossbar, let's say 1,000 processors, 1,000 memories, it's too expensive, essentially, in terms of latency as well as cost. The question is, can we get lower cost than a crossbar, yet still have low contention compared to a bus? We don't want the bus. We don't want the crossbar either. How do we get something in between? And that's essentially why people have invented these multi-stage networks or indirect networks. This is an example. Essentially, multi-stage logarithmic networks, usually they're logarithmic for the reasons that you will see. For example, you have here 8 things connected to 8 other things. Let's say 8 processors connected to 8 other banks over here. And you basically have 3-stage network log 2 to the 8 because each router has 2 inputs and 2 outputs, right? That's the logarithm part. If each router had 4 inputs and 4 outputs, you would have actually 2-stage network. Okay, but basic idea of multi-stage logarithmic networks is you have indirect networks with multiple layers of switches between terminals or nodes. So you can see that this is one example. And some of the things inside this network are purely switches, right? These are the endpoints over here. These are purely switches. I guess these are endpoints and switches over here. This has no function other than switching, right? Okay, so here the upside is now your cost is not n square anymore, right? Your cost is n log n, and you can see that because each stage has you'll have log n stages, and each of them you have order n type of switches, and latency is log n because you have a log n number of stages, right? So as I said, for an 8 input, so for an 8 node to 8 node communication with 2 by 2 routers, you get log 2 to the 8, and that's 3 stages essentially. And there are many variations of this. Again, I'm not going to go through the details of how these variations come about. They all have slightly different properties. You've seen butterfly earlier. There's Omega network. This is an example of an Omega network. There's Baynes, Banyan. They're all used in different supercomputers in the past. If you're really interested, you can take a look at the respective papers and respective supercomputers. Okay, let's take a look at communication issues over here. So let's assume that processor 7 wants to communicate with bank 7. There's only one path it can go through, as you can see. And let's assume that processor 1 wants to communicate with bank 6, which has nothing, there's no conflict, right, over here. But because of the way switches are wired, you get contention, conflict. Assuming these, let's say, messages arrive at the same time to the switch, they will conflict, and this switch will need to delay one over the other, right? That's the idea. So this sort of conflict doesn't exist in a crossbar, right? Make sense? Because these are 2 different destinations, and by definition, crossbar, different destinations have complete parallelism, complete independence, regardless of whoever is communicating with them. Here, these are different destinations that conflict because we are lower cost than a crossbar, right? So all of these networks have different types of conflict patterns depending on how switches are wired. Okay. Okay, so there, I already said this actually. The reason we get this less cost than a crossbar is because we're restricting the concurrent transaction and response pairs compared to a crossbar, or sender or receiver pairs. Let me put it that way: sender or receiver pairs compared to a crossbar. And that restriction enables us to be less costly, but also enables us to have more. Maybe enables is not the best word, but also caused us to have more contention. Right? Okay. Now the interesting thing is, usually the way you build switches is they're crossbars. So this is a 2x2 crossbar, as you can see, right? If you look inside each switch in this particular multi-stage network, it's a 2x2 crossbar. A 2x2 crossbar is much easier to build than an 8x8 crossbar, right? So we're building a multi-stage network of 2x2 crossbars to enable communication across 8 nodes across the entire network. And this is a butterfly. Again, this is a specific pattern, butterfly pattern. Okay. There's another thing that I want to cover over here, which kind of makes sense to cover, which is independent of the network topology, actually. It's a higher level protocol decision. And that's the idea of circuit switching versus packet switching. Have you guys discussed this in any other course? Circuit switch networks, packet switch. Okay, which course? Okay, communication networks. How many people have taken communication networks? Okay, not everyone. That's good. Well, not necessarily good, but that's how it is. a lot of what we discussed may be covered in communication networks also. So circuit switching, essentially, there are 2 major ways of communicating between a source and destination at a higher, let's say, protocol level. One is you have a source, you have a destination, and you have a bunch of routers in between. One approach says, I set up the path completely between source and destination, and I dedicate, I call it a circuit. That path is called a circuit. And I dedicate that completely between that source and destination. And until the source or destination tears down that path, it's dedicated, and these 2 things can communicate. That's the idea. What does it mean to set up the path completely? Meaning you configure the switches to transmit the data before the data is transmitted. So for example, if you want to transmit between 0 and 7, what you do is you set up such that this input is connected to this output in this particular router, for sure. And then by configuring some muxes, for example, and then you set up this input to be connected to this output in this router, meaning in this crossbar, again, for sure. And then you set up this input to be connected to this input. Now you have a continuous path from processor 0 to bank 7, right? Or processor 7, some other processor 7. Now, if you set this up, what happens is you don't need to decide for every message, where should it go? If processor 0 is communicating with bank 7, it keeps sending packets or messages on that path. And there's no need for buffering since switching is static once the path is set up. Meaning you don't need to buffer anything because you don't need to make any decision once you set up the path. Of course, you need to have some mechanism to set up the path, which we didn't discuss, but there needs to be some way of setting up this path. So this is a very efficient way of communicating. It could be done in different topologies. We're looking at a multi-stage network topology over here. Now, of course, the downside is once you set up the path to be configured this way, you cannot communicate between 7 to 7 over here, for example, right? Or you cannot communicate between something to something else that requires exactly the same path, right? Because you set it up to be connected from here to here. Does that make sense? So basically, that set of switches is now dedicated to this source and destination pair, source and receiver pair. Okay, that's the downside, of course. We're going to see that again. Now, if you have packet switching, this is completely different. You don't set up a path. Every packet you consider independently in each switch, in each router. So basically, if you think about it, you have packets that hop from router to router. Every router makes a decision on which input goes to which output every cycle, pending the availability of the next required switch, and assuming you have buffers, buffer. So for example, if you want to communicate between 0 and 7, you send the packet, and then this router dynamically decides whether this can go here or not, based on what's happening over here, and based on what may be happening in the buffers over here. So every router makes an independent decision. There's no path setup, etc. Make sense? Now, this enables more flexibility because when 0 is sending message to 7, 7 can also send a message to 7, and each router can make a dynamic decision. Okay, in this cycle, I'm going to take this input and connect it to this output. In the next cycle, I'm going to connect this input to this output. There is no strict static setup of a path. If you had set up a path, you had to tear it down first until someone else can use it. Okay, so packet switch networks are usually more dynamic and more flexible. The downside is there's more overhead because every router needs to make a decision every cycle. Okay, so essentially, this is the summary of circuit versus packet switching. Circuit switching sets up full path before transmission. Packet switching performs routing per packet in each router. You establish route and then send data in circuit switching. No one else can use those links while the circuit is established or set. Whereas packet switching, you route each packet individually, possibly via different paths. It could be different paths, as we will see in more in networks that have a lot more path diversity than what we have seen earlier. If the link is free, any packet can use it. So that's good. Now, the upside of circuit switching is very fast arbitration because once you set up the path, there is no arbitration. Right? You set up the path, the thing flows. No buffering. I mean, I guess you could add buffering, but there's no need for it. Downside is setting up and bringing down the path takes time. And path cannot be used by multiple flows concurrently. So flexibility is low. Packet switching is potentially slower because you must dynamically decide every cycle in each router. You need to handle contention, maybe via buffering in some other way. Whereas in packet switching, there's no contention because you don't allow contention, right? By design of the setting up the path, you say you cannot set up a path, so there is no contention. I guess that is the contention actually over there, but you don't need to handle it on a cycle-by-cycle basis, essentially. So there's no setup and bring downtime. That's the big advantage of packet switching. You can start sending right away. And also it's more flexible. It doesn't underutilize links. So with circuit switching, you could underutilize link when there's a lot of concurrent sender and receiver pairs that need to communicate and that actually conflict in the paths. Okay, so this is an important discussion that we should have had, should have at this point. But think about circuit versus packet switching as something that's independent of topology. Some topologies are more amenable to circuit versus packet switching, but this is really a higher level protocol on how a message gets sent to its destination. Yes. Mm-hmm. Yes. Circuit switching, actually. I thought you were going to say circuit switching, but yes, circuit switching. There's circuit switch topology, yes, to make it simpler again. The goal is to make it simpler. Yeah. Yeah. Mm-hmm. Yeah. It's not that fancy, but there is room for improvement. Maybe you can comment on that. Mm-hmm. Yeah. Yeah. So there's room for improvement, basically. I agree with you that there may be a better way of actually scheduling the paths. Okay, so these ideas have been employed in many systems, including the internet. But this is an example of on-chip networks in Tylera. This is a nice paper that talks about different on-chip network architectures. And it's also good to think that there's not a single network in a system. There are actually many different networks for different communication patterns. And this is one example of that. We're going to see more examples of that. In this particular case, the topology of, I think this was 100 cores, if I remember, but they show a smaller picture over here, 3x3 example. Topology is two-dimensional mesh network, we will see. Simpler than what we have seen. Not bus, of course, not simpler than bus. And there are 5 networks over here. 4 of them are packet switched. 1 of them is circuit switched. And the reason they have a circuit switched on one of them is so that they can actually enable low latency, high bandwidth communication for streaming data. For example, if one node wants to write to memory, or one node wants to transfer gigabytes of data to another node, you basically set up the path and pump the data every cycle, and you don't need to have any dynamic switching overhead for gigabytes of data, let's say, right? If you think about it, this circuit switching amortizes the cost of large amounts of data transfers because it doesn't do dynamic switching for every single small packet, which may be 64 bits. Imagine doing dynamic decision making for every 64 bit of 64 gigabytes of data. That's a lot of decisions that you make. If you set up a circuit, you just pump the data every cycle. There's no need for routing or switching. So that's the reason they have it. The others are packet switched networks. And you can see that there's a network for cache request packets. There's a separate network for cache response packets, because requests and response are very different characteristics, right? Requests are small. Responses are data. Requests are control packets, usually address and command packets and coherence packets. But response is different. It's much larger. So the networks actually have different characteristics. There's also for I/O packets, input-output, a separate network. And there's also a separate network for messaging between cores, if you want to do inter-processor interrupts, for example, or some other communication across cores. So it's good to keep this in mind. They're actually, all of these ideas that we're going to discuss are employed in different ways, and they're also combined in different ways in different types of processors and systems. Okay. So this is another multi-stage network. I will not go into the details of different networks, but this is actually older than what we have discussed. This is one of the seminal papers in computer architecture by Janak Patel, who also happens to be the major author of the MESI protocol paper, if you remember, with his student Papa Marcos. That was later than this paper. So you can see that people are actually working on scalable multiprocessors in 1970s, 1980s, and they invented a lot of interesting things because they were working on that. It's kind of like the processing in memory today, right? People are working on processing in memory. They're inventing a lot of things. In 1970s, it was like, how do you scale up these multiprocessors to very large scale systems? And they invented the Delta network. This is one example. And there's a single path from source to destination. Each stage has different routers, which is an interesting choice. So you cannot basically replicate the same router across all of the stages. That's one downside also potentially. But this was the first paper in the area. And it essentially proposes to replace costly crossbars as processor memory interconnect. So if you want to read one very early paper, this is the paper to read. And then there are a bunch of other papers. This is actually a very nice one also. This is the Omega network. It's very similar to the Delta, except all stages are the same. It basically simplifies the routers. Well, the routers are actually the same. It's 2x2 routers, but it simplifies. It doesn't have heterogeneity in the routers across different stages. So it's easier to build in that sense. But the contention patterns may be different, of course. This was used in NYU Ultracomputer, which is actually a very nice paper by Schwartz and Gottlieb et al. There's another reason to talk about that, because these folks actually did some things really interesting in the 1980s, which is doing operations inside the network. So today we're talking about operations inside memory, right? Which is also an old idea. But these folks actually implemented this in a real supercomputer. And the idea was to actually simplify some of the things that we have discussed in previous lectures. If the router can operate on a memory location and update the data value of that memory location and give it to someone else who requests it at the same time, you don't need to go and update the memory location on the memory side every time. So to reduce the contention on the memory and the latency on the memory, do some of the updates that are amenable for doing the updates inside the routers. Essentially, each switch is capable of doing fetch and add operations in this computer, NYU Ultracomputer. Fetch and add is essentially, you for example, have some sort of primitive to test and set a lock, right? You can convert it to a fetch and OR operation. That's one example. Essentially, you return M and replace M with M plus I. Okay, that's the idea. It could be fetch and OR, fetch and whatever, fetch and multiply. You could come up with different things. And this is common when you actually do synchronization in parallel processors. For example, when processors modify a shared variable, let's assume that you're doing task partitioning, and each processor wants to get a chunk of I from an array. And it depends on which processor accesses that variable first. The first processor gets the beginning of the array M, and it's going to operate on M plus I, those indices, essentially I indices, and then replace M with M plus I so that the next processor sees M plus I and gets the portion of the array that starts from M plus I to M plus 2I, right? So all of these operations can be done in the network, essentially. Of course, there are some mechanisms to make sure that you don't do wrong things, but this is an idea that's well ahead of its time. These are actually coming back in a lot of AI accelerator systems. People are doing this sort of stuff these days. Hopefully they're not forgetting the past. Okay. Forgetting the past means, these have been done in 1970s, 1980s, and they may think that they've invented this, but not exactly. So it's good to think about people who have walked this earth that have done actually really great things, in my opinion. So even processing in memory is not new in that sense, but it's not as well examined compared to many things. Okay, so Butterfly is another example. It's actually equivalent to Omega network. This is used in some supercomputers of its time. You can read about them. And you can see they look like Butterfly. So a lot of these multi-stage network actually have some sort of saturation problem that I'm not going to go into. If you actually have a lot of contention, they saturate. For example, if this node, if for some reason this node becomes a bottleneck, you may not be able to transfer a lot of data across the network, even though there is some parallelism because of the way switches are connected. So how do you ensure that? Randomizing route selection, if you are able to do that, helps, but that depends on how the switches are wired. Throttling helps. We're going to talk about throttling, meaning if you actually have some node that's injecting a lot and causing a lot of contention, that helps. We talked about fairness via source throttling a long time ago, for example. The ideas are actually similar. So it's really important to manage these shared resources to minimize the loss of parallelism that you get, because there's some particular bottleneck in the network that actually causes a lot of contention. Right? And these are real issues actually that you see in real systems also. You may actually find that some node is very contended, and as a result, your system performance tanks. Okay, this is a review. I will not go into this. You can study this on your own. We've covered crossbars. We've covered multi-stage logarithmic. We have not covered meshes. We're going to cover that. But meshes are actually direct networks that look like this. Every node is connected to its neighbor with a switch. And you can see some of the properties over here. So a mesh actually reduces the cost to ON, but it has latency issues as it grows, as you can see. Their latency is O square root of n, as opposed to O log of n, right? It's good to think of that. So we're going to look at mesh, but we're going to look at other things also. Okay, so before I go to mesh, I should say that what we do is actually really relevant to what is being implemented today. GPUs, for example, have indirect networks. I will not go through all of the evolution of GPUs. They have both hierarchical networks and indirect networks. And this kind of looks like a fat tree, which we will also see. But this is the more recent GPUs. I think it's Blackwell. You can see that there's an indirect network across different GPUs over here. These are purely switches to connect the GPUs to each other. And if you look at the hot chips presentation, they give you a little bit more interesting things. You can see that the switch nodes are blue. You can see that the 72 GPUs are like this. And I think they have this NVLink protocol, NVLink 5 protocol, to connect the GPUs and the switches and the GPUs. And you can see that this is some sort of indirect network that enables this sort of communication. And these are actually happening at very high bandwidth. And if you want to scale this up, actually, there's another level because 72 is not enough. You need to actually have another level, and that actually goes to the PCIe, etc. Okay. Any questions? You can read more. We're going to look at some other things. People make different choices. Okay, let's talk about rings. So we're still talking about topology. And our goal is to, again, reduce cost. And let's take a look, let's take the perspective of what is the minimal thing that you can do beyond the bus. Right? Because bus is too, let's say, non-scalable. If you want to have a little bit more scalability, how would you connect things? And ring has come to people's minds, and it looks like this basically. Every node is connected to every consecutive node, and then eventually there's a wraparound connection. Each node is connected exactly to two other nodes. Nodes form a continuous pathway such that packets can reach any node. So this is cheap, as you can see. It's not as cheap as a bus. You have ON links. N is the number of nodes, of course. But they're shorter links. They're not as loaded as a bus. That's the good part. The latency is high, unfortunately. It's not as short as a bus, but you're not as loaded as a bus also. Think about that. The latency is ON on average. It's not easy to scale. I'll put the term bisection bandwidth, because bandwidth doesn't increase with the number of nodes. It's a very different reason why buses are not easy to scale, though. Here, you could keep adding nodes. Your latency increases, and your bandwidth doesn't increase. But you could keep adding nodes. In that sense, it's easy to scale. But its bandwidth doesn't increase, and your latency increases if you keep adding nodes. So when we talk about scaling, it has different also connotations, right? What does it mean not to scale for a bus? Bus actually has very bad electrical loading contention. This may not have that many issues, but latency increases. So this is, as a result, this is actually used for scaling many small-scale multiprocessor networks. Many commercial systems today use rings, and we will see some examples of it. Not exactly this ring, though. This is one example of a ring, of course. Okay, unidirectional link. Let's go into a little bit more detail in rings. So essentially, in a unidirectional ring, you have a single directional pathway, meaning you have only one direction, left to right, let's say, clockwise, whatever you want to think about. I think this is clockwise. There's no counterclockwise direction. There's no other ring on the other side, other direction, basically. So you have ring stops over here, which are essentially 2x2 routers, and you can see how they're connected. You can get something from the network into the node. You can inject into the node, or you can pass through. Essentially, you can inject into the network, or you can pass through. And if you want to send a message from here to here, clearly you need to go through all of these nodes. That's the worst case. So this is simple. Topology is simple. Implementation is simple. You get reasonable performance if N is low, and performance needs are also moderately low. You still have ON cost in terms of links, in terms of routers also. The average hops are N/2, assuming there's equal communication across different pairs of nodes. And latency clearly depends on the utilization. So this is actually nice and clean, but it's not very scalable for the reasons we discussed. So unidirectional rings are actually not employed as much because of the asymmetry, right? If you want to go from here to here, that takes a long time. Whereas if you want to go from here to here, it's one hop, right? So why wouldn't we have another ring that goes in the other direction, which is essentially two rings, if you think about it, bidirectional ring. You could share the links across them. Essentially, these are multi-directional pathways or multiple rings. This reduces latency, improves scalability, but you have slightly more complex injection policy. You need to select which way to go, counterclockwise or clockwise. And this could be based on multiple decisions, contention decision, for example. If you know some information about, oh, if I go through clockwise, there's a lot of contention over there, so let me go through counterclockwise. But this requires information about how contended different parts of a network may be. So I'm kind of getting ahead of myself, but this is actually how the decisions are made dynamically in real networks. Okay, so these are employed. This is Intel Alder Lake. You can see that it actually has a bidirectional ring across however many processors it has. I think they have 8 of these big cores and 8 of these small cores. You can see it's an asymmetric multiprocessor. And you can see that these are actually not cheap also. These are big. But they're at least easier to design than a crossbar. If there was a crossbar over here, that would be huge. Okay. So if you want to scale rings, there's actually a nice way. So any network can be scaled by adding hierarchy to it. So for example, you may have a bus, and you may have hierarchy of buses. you have, for example, 4 processors connected to each other with a bus. And let's say that this is a 4-processor group, and you want to connect 4 different 4-processor groups with another bus, right? And then you want to connect that with another bus to another 16-processor group. So you can actually scale things with hierarchy. Buses are still not good because as you keep adding things to the hierarchy, electrical loading keeps increasing. Rings are nicer in that sense because you can scale things in a little better way. So you can see that there's a 4-node ring over here. And there are 4 4-node rings. And you can connect those 4-node rings using another ring with blue stops over here. Those are not nodes, just switches, as you can see, right? This is another way of connecting the same 4-node rings with a more expensive global ring, let's say. And this is another way of connecting those 4-node rings with 2 global rings. And all of these have different properties in terms of contention, cost, latency, etc. But all of these are made to scale. Instead of building a 16-node ring, which was bad for latency, etc., you basically have a hierarchy of 4-node rings, right? Okay. And this is the 8x8, 64-node ring. This is one way of doing it, of course. There are multiple ways of doing it. So this is actually an area, I think, where people should investigate more. This is more scalable in general. Lower latency, because what you can do is this ring. So for example, if you want to go from this node to this node, it could be very fast. You hop onto this ring, hop off here, and go to that node, right? That's the idea. Of course, hopefully these are bidirectional rings. That's the assumption. Unidirectional is not good in general. But basically, the bandwidth of the higher level rings, or let's call them global, or the higher level rings, can be higher than the bandwidth of the lower level rings also to support that sort of communication. So you can customize this. Of course, this adds more complexity, but it could be also easy to lay out. So you can see one example. This is quite regular. It's relatively easy to lay out with, I believe, 3 metal layers, at least just for the interconnects that we see over here. So it's good to think about this. This is an area that I like a lot. And we've done a lot of research in hierarchical rings. And in our papers, we've shown that actually these, if they're carefully designed, they could be actually much more energy efficient. And sometimes high performance topologies, depending on the type of workload you have, compared to even more complex topologies like meshes or toruses, as we will see. So I'm a big fan of hierarchical rings, actually. It's good to think about this. There's more work that needs to be done in this area, and this is one paper that we've written. The good news is people have actually implemented very similar to what we have proposed in these 2 works. It's essentially hierarchical rings with deflection routing, which we will see. Essentially, not so much buffering. You don't have buffering. You minimize the buffers as much as possible. And you have some mechanisms to make sure that there's no deadlock or live lock in your links, which we're going to define later on. And this was implemented in Huawei's Kunpeng 920 processor, which is essentially a machine learning accelerator. And you can read more about their paper if you're interested. It's essentially a bufferless hierarchical ring. They call it multi-ring NOC. That's very fascinating. Okay. So let's talk about meshes. So you've seen meshes before, but let's talk about them. So rings and hierarchical rings are actually very interesting. Comparison between some of these topologies becomes a bit challenging because hierarchical rings actually introduce hierarchy. Meshes don't have hierarchy, but they could also be built with hierarchy. But let's take a look at them. So essentially, as I said earlier, each node in a mesh is connected to 4 of its immediate neighbors, north, east, south, west. The edge nodes are poor because they lack 1 or 2 neighbors, as you can see. We're going to fix that problem with Torus later on. You have very short and regular links, as you can see. It's very similar to hierarchy rings in the end. But you don't have rings, basically. You have connections to all 4 of your neighbors, as opposed to only 2 of your neighbors. Right? You have ON costs. Average latency is square root of n. It's also easy to lay out on chip, regular and equal length rings. There's path diversity. I mean, this is true for some other networks also, but especially important in meshes because there are many ways to get from one node to another. Right? If you want to go from this node to this node, You can take any different paths that lead you there, right? You can go through any switch that lead you there. You can even take the scenic route, as we will do in Bufferless routing. You can go around like this and do whatever loops, and then eventually get to your destination. That's not the minimal path, but you could do that. If you constrain yourself to minimal paths, meaning minimum paths that lead to the minimum number of hops between a given source and a given destination, you have many choices also, right? I could construct many minimal paths over here. I'll let you do that, but it's possible. Not as easy in rings, unless you add a hierarchy. Once you add hierarchy to rings, then your path diversity also increases. So it's good to think about that. Hierarchy actually enables you to do something bigger than a single topology. And with hierarchy, you can mix topologies also. You can have a bus, and then you can have a ring, and you can have a mesh. Right? It's good to think about that. This is not easy to explore also, this whole space. Okay, so path diversity is important. So this is used in many prototype networks, and we'll see that some AI accelerators also. It has not made it into real production CPUs yet, I think, but it may eventually, because the cost is higher than rings essentially. People didn't go take the step to go from rings to meshes yet. And I believe if you introduce hierarchy to rings, maybe there's not too much need to go to meshes, but it's good to think about that. Okay, so mesh has one big problem though. And the problem is in the edges, it's not symmetric, right? Everything here is symmetric except for the edge nodes, right? Meaning if you want to go from this node to this node, you cannot do that easily by wrapping around. Right? So what happens in mesh is if you have a lot of contention, traffic is pushed inside because you cannot go outside and wrap around, right? So contention patterns are actually not so nice. And performance as a result becomes very sensitive to placement of task on the edge versus middle. If you're over here, your bandwidth is by definition is lower, right? Because you have only 2 neighbors. If you're over here, you have 4 neighbors. Right? By definition, your bandwidth is much higher. Right? So to avoid this problem, people have designed Tori or Torus, the singular, and it looks like this basically. It fixes the problem by adding wraparound links in meshes. And this is an example of 4x4 Torus. And now you have even higher path diversity and bisection bandwidth than mesh. So what is bisection bandwidth? You basically find the lowest bandwidth point and cut. In a mesh, lowest bandwidth point happens to be over here, right? So your bisection bandwidth is actually very low in mesh relatively. Here, your lowest bandwidth point is equal everywhere, regardless of wherever you cut. So you're actually very symmetric. Okay, so downside is of course higher cost because you have more links. And now you have another problem. How do you lay this out on chip, right? Because seemingly you have unequal link lengths now, right? Mesh was nicer because you could replicate the same thing, except you don't connect the edge nodes to some nodes, right? That's easy. Here, what's an edge node? There's no edge node. If you have 2-dimensional substrate, how does this go, right? It's good to think about that. Now, the good news is people are creative and they come up with ways of connecting things such that you can weave the nodes to make internode latencies approximately constant, maybe not perfectly constant, but this is one way of actually designing one cross-section of a torus, right? One row. So you can think about it. Okay, so meshes are used in modern accelerators. So this is Tesla Dojo, their accelerator chip. They have a huge mesh, pretty expensive, I think. But it's a huge mesh. I don't remember how many, maybe 1,000 processors or so. And they also figure out, okay, if I can read this thing, these are the accelerator processors, some sort of SIMD mechanism. And they have some interface processors on the side that interface with the host system to do some other operations, connected to the outside world, etc. But they also realize that mesh is not very efficient if you want to communicate between edges. So they actually have some special links that look like this to enable communication between these interface processors. So they have meshes that connect the accelerators, ML accelerators, and to connect the interface processors, they have something that looks like this. and I don't remember what it was. It's some sort of Ethernet switch. They don't talk about the topology, I think. So it's good to think about the fact that there are different types of communication mechanisms that you need to build in a real system. So Torus is also used in modern accelerators. So this is Google TPU, and they actually added a Torus. It used to be a mesh, and they made it a Torus in more recent TPU. Let's see what, and this is their Torus essentially. And they also have optical switching in this particular case. And the reason they wanted to have a Torus was, I think actually they were 2D Torus, and they turned the 3D Torus in the latest accelerator. And they wanted, essentially, they wanted to scale up the system. I will not go through reading all of this, but this is 164 64 accelerator system. And I think they have 64 of these 64 together to form, what is 64 times 64? That's 4,096. Okay, that's good. So they have 4,096 chips, essentially. And this is a 64 chip version of it. And then there's a way of connecting these 64 with every other one, 64 as well. But again, it's a Torus in the end, even though the description is not very easy to follow in the paper. It's a good paper though, so I'd recommend reading. Okay, so let's continue, and then let's actually take a break after we finish topology, because this is fun, I think. Okay, you can imagine many topologies. People have actually designed trees. We've seen the H tree, clock tree, and these now become a little bit more specialized. So trees are nice because they're planar, hierarchical. They're good for local traffic, especially if you're communicating between these tree nodes a lot, for example. It's good for handling that local traffic. And if you want to do more global communication, if you want to communicate, for example, from here to here, your bandwidth level may increase. That's why it's called a fat tree, meaning higher levels of the hierarchy have higher bandwidth connections, potentially lower latency connections also. So the latency is all log n over here because it's a tree. It's cheap, O(n) cost, it's easy to lay out. The downside is actually its root can become a bottleneck. And the way you solve this bottleneck is by having more bandwidth allocated to the links at the higher levels. So fat trees essentially avoid this problem, and connection machine, which is essentially an old supercomputer built in the 1990s, avoid this problem. I'm going to talk about their network. So it's essentially a fat tree based on 4x2 switches. You can see the switches over here. There's one level of switches over here, and there's another level of switches over here, and there's some outside connectivity that enable. The routing is randomized on the way up so that you don't have contention as much as possible. And this machine also supports a lot of operations in the network, combining multicast, reduction, aggregation operations, for example. For example, if you want to add all of the values that are computed by these bottom nodes, this is a nice reduction operation that could be done in the switches in the network, right? Each switch can actually aggregate the values coming to it and pass it on to the higher part. And then they also aggregate the values. And eventually the root has the final sum, right? If you're summing all of the values that are computed by the leaf nodes. So some sort of computations and communications fit this much more nicely. The downside is not all computations and communications are that sort of reduction or aggregation operations. And when you cannot map your computation and communication nicely to the structure of the topology, then it becomes harder to program these things, and it becomes harder to get high performance. Good to consider that. And this is actually the fat tree paper. You can take a look at it. Okay. So Hypercube, this is the paper that I mentioned from Chuck Seitz. This is another, this is actually a very innovative network, in my opinion, at the time. We're talking about 1980s. This is an n-dimensional cube, or n-cube. And you can see that it looks like this, basically. This is the 0-dimension, 1-dimensional, 2-dimensional, 3-dimensional is what we call cube. And this 4-dimensional cube, Hypercube. And then you can make it 5 or 6-dimensional, as we will see. Now, the upside of this is latency is log n. Radix of each router is log n, which we didn't consider a lot, but radix is also important, how many routers you connect with. And the goal here was to actually minimize the latency across any single source and destination pair. And they actually achieve this with this. And number of links is O n log n. So we get low latency, but unfortunately, this may become hard to lay out in 2D and 3D. But there is a way to do it. This is the Cosmic Cube paper. And it was actually a 64 node, which is small by today's standards. We've seen 72 node GPUs, right? Which was not a hypercube also, as you have seen. But I think the Torus starts looking like that, but it's not a hypercube also. Torus is easier to lay out. Maybe someone will build this again later on, but who knows? But this is actually the 64 node machine, and this is how they laid it out. And these were actually cables, real cables. So each of them is a processor, and somebody needs to do the cabling. And if you get it incorrect, then things are wired incorrectly. This actually happens in real supercomputers, by the way. Somebody wires things incorrectly, and you have to debug it before it becomes operational. And that could be the beauty of optical connections, actually, because you don't need to wire real wires. But this is very nice, I think, as you can see. It's good to read also. I would recommend reading this paper. So this is the motivation. Let me see. Yeah, I think I've already said a lot of things that's said, but I'll recommend you to read the paper because it's a nice paper to read. Okay, this is a very good place to stop, unless there's a burning question that we have. Okay, no burning questions. So let's take a break until, let me see, until 14:58, and then we can continue with routing. Okay, I think we can continue. So we just covered some basics in interconnection networks, and we covered topology. There's a lot more to study on topology, and this is an area where more research needs to be done, in my opinion, especially with the communication patterns that we have in modern workloads that are increasing the stress and contention on our systems. Any questions on topology? Okay, then I'm going to move on to routing, which is actually a big area also that is not independently studied of topology usually, because topologies affect routing mechanisms. So routing is actually how you deliver one message from a source S to a destination D, right? And there are multiple aspects to this. We're going to focus especially on the algorithms, but we're going to talk about the mechanism first, because mechanism is also interesting, right? And there are three major mechanisms for accomplishing routing. This is you can think of this as a method for routing on top of which algorithms can be built. Arithmetic routing mechanisms, essentially you use some simple arithmetic to determine where to go next in regular topologies. So if you have a mesh, for example, you're at node 0, 0, row 0, column 0. And if you want to go to row 10, column 10, you can basically do some arithmetic and figure out that you need to traverse 10 links up and 10 links to the right, for example, right? Depending on where row 10, column 10 is. And then you can basically do some arithmetic to decide whether you go up first, right next, up next, right next. So basically, at every single router, you basically do some arithmetic to decide whether you go up or right. Of course, you can decide to go left and down also if there's some contention, but we're going to see that. Essentially, you do some arithmetic to determine where to go next. And clearly, this is easy to do when doing routing. You don't need complicated tables to store your path, to store your route, if you will. You just look at the source location and the destination location, and wherever you are at this point, actually, maybe the source doesn't matter after some point, depending on whether you get dropped or not. But you basically look at your current location expressed via some sort of coordinates, and you compare it to the destination location expressed via some other sort of coordinates. You do some arithmetic, and routing algorithm then decides which path you take. Okay, so we're going to see, for example, dimension order routing in meshes and tori. Dimension order routing means you have X and Y dimensions in a two-dimensional network. You traverse the X dimension first, and then the Y dimension next. That's the idea. You order the dimensions in some way, and we're going to see why that is the case. The main reason is to avoid deadlock, actually, as we will see soon. But the dimension order routing operates based on simple arithmetic mechanism, and this is usually very simple. Okay, source-based routing is completely different. You don't do area arithmetic. Basically, at the source node, the route is specified. At every single switch in the route, you basically have an output port to take. So if I'm in the first switch, whatever that first switch may be, when you actually get injected, I go south. In the next switch, I go west. In the next switch, I go east. In the next switch, I go whatever, right? Clearly, this may not be very adaptive, but then this could also be updated depending on where you are. Basically, you encode a list of nodes to visit that will enable you to go to your destination. This is called source-based because the source actually encodes this. Usually, this is nice with circuit switching type of methods, but it could also be expensive because this needs to be encoded in the header of a packet, for example. And finally, there's table lookup based, meaning at every router, you can look up a table to decide where to go next. You index a table, and the table says you go west or you go east. And this could be actually dynamic because you can make a sequence of table lookups based on the inputs. And this is also complicated. This complicates the router, as you can see. Okay, source-based. If you do source-based, completely source-based routing in the pure form, your switches are simple. Your switches need to have no control state. They don't need to do a table lookup. They don't need to do arithmetic. They just need to strip output port off the header and basically follow what the header says in the packet. The downside is large header, basically. The source needs to encode that inside the header. The upside of table lookup based, you have a small header. You just need to know which destination you're going. But the switches are more complex. Okay, today, basically, people can use different methods. Source-based is usually not preferred because of the huge headers in general, especially with large-scale networks. Arithmetic is hard in the sense that it may not adapt to the faults. So there's usually some sort of table lookup that happens in routers. Internet routers, of course, there's huge table lookups that happen. But even in on-chip routers, if you want to avoid faults, it's very difficult to do that with arithmetic solely, because then you need to encode which things are actually arithmetically not possible to reach because there's a fault along the route. And that brings you back to table lookup. You need some sort of tables, basically, to avoid faults. Okay, so that was the mechanism. On top of a mechanism, you can build an algorithm. Essentially, and there are three types of algorithms. One is deterministic. Essentially, you always, for a given communicating source and destination pair, you always choose the same path. That's why it's deterministic. Always choose the same path. Oblivious means for a given source and destination pair, you choose different paths at different times, but without considering the network state. Basically, you're oblivious to the state of the network. And we'll see why this could be advantageous. And finally, adaptive. You can choose different paths when you communicate between a given source and a given destination at different times. And the goal is to adapt to the state of the network. Sometimes you go this way, sometimes you go this way, based on where you think the contention is high or low and how fast you can get to the destination. Right? And all these three algorithms are also employed. Once you're adaptive, then the question becomes, how do you adapt? Right? What kind of information do you use? Is it local feedback, meaning you look at the next router and figure out which router is not congested, which router has more buffers available, which routers have even buffers available? That's local, basically, immediately local routers. Global feedback means you look at the different regions of the network. Which region? Maybe you're trying to get to region X, right? And there are different regions that you can get to the network from, ABC or QPR, let's say. Which one do you follow? You basically have some sort of information communicated and aggregated across the network that tells, oh, ABC is less congested because there are fewer packets inside the routers over there. So you may choose ABC that way, based on the characteristics of the network. Of course, whenever you adapt using local or global feedback, especially global feedback, you need to collect this information. You need to communicate the information to the routers, and you need to store the information. That information should not be very stale, meaning you need to update this information as things go, as things change. So this sort of feedback is actually nice to have, but it may not be easy to have, especially in a very large scale network, right? You may know the local feedback relatively easily, but the global feedback far away is not that easy. Especially to keep it up to date is not easy, because this is also a communication, right? Think about how do you communicate this information? There needs to be a network to communicate that information, right? So there needs to be a network, control network, usually called, to collect that information. And if that network gets congested, you may not have correct information, right? So essentially, it's an example of who watches the watcher problem, right? And it's not exactly dependability, but it's more quality of information that you get depends on the watcher, which is really the thing that's monitoring the network to figure out which parts are congested. Okay, there's also another way of adapting. When you adapt, do you always stick to the minimal paths, meaning the minimal number of hops to go from source A to destination B? Or do you sometimes take non-minimal paths, meaning you don't take the minimal path sometimes, right? Of course, if you adapt minimally, minimal adaptive algorithms, they're usually more restrictive, right? Because there are a small number of minimal paths when you have path diversity. But there are many non-minimal paths. If you think about a mesh network, right? Non-minimal paths are essentially unlimited if you think about it, right? I guess once you're non-minimal anyway. But it's essentially unlimited because two-dimensional mesh, you can essentially circle around 100 times and then eventually get to your network, right? That's essentially a non-minimal path. Another non-minimal path is basically going against, taking an output port that actually takes you far away from your destination is by definition a non-minimal path. So if you adapt non-minimally, you can avoid congested areas more easily. If you stick to minimal paths, congestion becomes harder to avoid. Okay, Hopefully this gives you an idea. And clearly there are many, many algorithms that people have developed. I'm going to look at several of these. So deterministic routing, all packets between the same source destination pair take the same path. Dimension order routing is one example of this. You first traverse the X dimension and then traverse the Y dimension. And this is used in many on-chip networks as well as many supercomputer networks in Cray 3D, T3D systems, for example, XY routing. And this is very simple. It gives you deadlock freedom. We're going to talk about that in a little bit because it doesn't allow resource cycles and resource allocation. We're going to talk about that. Whenever you have minimal adaptive routing or some sort of routing, you need to make sure you have deadlock freedom. The downside is it could lead to high contention. It's clear it doesn't exploit path diversity. So let's take a look at that. Maybe someone can help me switch to this thing. Okay, while they're coming, I'll construct my mesh network. Let's do 4x4. And this is a mesh. Okay, I guess I should have really put everything because 4x4 is not that hard to build. Okay, so this is your mesh network. Let's assume that you want to go from this node A to this node C. Well, I don't know, whatever, X, why not? XY routing says you first traverse the X dimension, which is this. This is X. And then you traverse the Y dimension. This is Y. And based on simple arithmetic, you go to the next until your column is the same as the column number of the destination. You basically make progress one by one in the rows. You go to the next column, right? That's the idea. And then you go to the next row, right? So it's arithmetic-based routing, clearly. So what you do is, do we have colors? We have only red. Interesting. And yellow. And blue. Okay, not bad. We could construct the whole thing. So you basically traverse this way. You go to the next router on the right, and the next router on the right, and next router on the right, and then you go traverse the Y dimension next. Okay, so that's XY routing for you. Clearly, this is the only path you can take from A to X. Clearly, this doesn't exploit path diversity. And if you don't exploit path diversity, one issue is contention, right? Now you have B, who also wants to transfer to, I don't know, Q, let's say. Because of XY routing, it needs to traverse X first and then Y next. You can see that there's contention over here. They're both needing the same links. And because of our routing algorithm, we're not adaptive by definition. Whenever they inject at the same time, they have some contention on the same input port over here, one of them needs to wait because they both need the same output port. And they cannot take some other output port. They cannot take the scenic route basically, because this is our routing algorithm. It's XY routing. And then there may be C. Well, C doesn't want to communicate to Z. And now you have more contention, right? So you could keep constructing these cases, and there could be actually even more contention. Okay, I'm going to do P to X, for example. Then you have, again, more contention over here, right? Basically, these links get contended, even though there are many, many other ways of communicating. This could have gone Y first, and then X direction next, and taken this path. This could have taken this path, for example, right? So basically, path diversity is not exploited with this sort of dimension order routing algorithm. Hopefully that's clear. But dimension order routing is minimal, but it's not adaptive, right? It's minimal, not adaptive, deterministic. Okay, so how do we get back? I guess I share, or do I do something else in addition? Maybe I do something else in addition. Okay, this may come back, you know. Watch out. Thanks. Okay, thank you. So I think I've already said all of these over here. It doesn't exploit path diversity, but it is deadlock free, and we're going to see that soon. Okay, deadlock. Deadlock is actually the fact that there's no forward progress. It is caused by circular dependencies on resources. Basically, if you can form a circular dependency where each packet waits for a buffer occupied by another packet downstream, and there's a circular dependency such that you cannot make progress, that's a deadlock. So for example, in this example, we see, let's see, this packet 1 wanting this resource. It needs to go over here, but it's occupied by packet 2. Packet 2 needs to go through this output port, but that is occupied by packet 3. Packet 3 needs to go through this output port, but that is occupied by packet 4. And packet 4 needs to go through this output port, and that's occupied by packet 1. Now we formed a circular dependency, right? Everybody needs the buffer downstream that is occupied by someone else, and there's a circular dependency across the transitive following of those dependencies. Sounds bad, right? So you should not run into this situation. Well, there are multiple solutions, right? How do you actually solve this problem? First, one way of solving this problem is never running into this problem, which is what XY routing does. Regardless of however not adaptive it is, and it is not adaptive, it doesn't run into this problem. Because everybody goes XY, everybody goes XY, there's nobody that goes YX, and as a result, you don't have a circular dependency. That's the idea. And you can prove it actually, but you need to read the paper for proving that. So basically, this is how you can handle deadlock. Not run into the problem, meaning avoid cycles in routing. You should not be able to build a circular dependency, and dimension order routing is one way of doing that. More generally, the idea is to restrict the turns each packet can take such that you cannot form this sort of circular dependency on resources. And there's a beautiful paper that I'm going to mention that has introduced the theory of turn model that talks about that. Another solution is to avoid deadlock by adding more buffering. Essentially, maybe you do have this circular dependency somehow, but you have enough buffering that you can escape that this doesn't happen, right? That's one other way of doing that. You have enough buffering that this never happens, right? Maybe expensive to build a system like that. And the third solution is detecting such a situation and breaking it. And one solution could be, okay, I mean, actually finding cycles in a graph may not be easy, right? There are people who have developed algorithms for finding cycles in a graph. This is a popular graph analytics problem. You need to analyze the network and figure out these resource dependencies. That's one way of doing this. You run a graph algorithm on the network and you figure out there's a cycle and you say, okay, I find the cycle, things are waiting for each other, so I break it somehow. How do you break it? You drop one of the packets, for example, right? Of course, your network needs to support retransmissions. If you drop one of the packets, that's one way of doing it. Another way of doing it is basically, maybe you don't run this expensive graph analytics algorithm that finds cycles, but you actually do look at, have timers on each request. And if one of them times out, it's been waiting for too long, you basically say something is wrong. Even though you're not sure whether there's deadlock or not, you just drop the packet and that frees up the deadlock. So a more randomized approach like that can help. Essentially, you preempt the buffers in some way. And there are multiple ways of doing that. You could do it expensively, you could do it cheaply, etc. In the end, it costs you performance. Right? That's the downside. That's why people try to avoid cycles in routing as much as possible. But these are also valid solutions. Okay, this is a turn model that I mentioned. The idea is to actually analyze directions in which packets can turn in the network from X to Y, Y to X, up to down, etc. And determine the cycles that such turns can form that could lead to a deadlock, and prohibit just enough turns to break possible cycles. So you can see, this of course depends on your topology, right? Mesh is different from torus, this is different from ring, etc. You can see that the form of possible turns and simple cycles in a two-dimensional mesh, if you have this sort of turns, all of the turns allowed, then you can form a cycle. In the XY routing algorithm, these are the turns that are allowed. Some of the turns are not allowed, as you can see, so the cycles are not possible to form because these dashed turns are not allowed. And then there could be other turns that could lead to deadlock, but you need to read the paper for that purpose. So this is a very, very beautiful paper that puts that theory, and it's a nice paper to read. Okay, so deadlock is important. This deadlock problem will turn into some other problem if you actually do a different form of flow control, right? Buffering is one form of doing flow control. If you don't have buffers, it's good to think about whether you have a deadlock problem. You have actually some other deadlock problem at a higher level, but you don't have this deadlock problem at a lower level, as we will see. Okay, so we have discussed deterministic. Let's discuss an oblivious routing algorithm. This is actually a beautiful, another beautiful paper from Leslie Valiant, who's a Turing Award winner for bulk synchronous processing and also parallel computing. Essentially, the idea here is you have a parallel computer and you have a big network. Assuming that different nodes are communicating equally with each other, one goal may be to balance the load of the network such that you can utilize the entire network. Clearly, there's an assumption over here. How do you do that? Right. And one way of doing that is using this algorithm that's named after Valiant. And the idea is to randomly choose an intermediate destination and route the packet to that destination first, and then route it from that intermediate destination to the actual destination. And between source to intermediate and intermediate to destination, you can use dimension order routing, for example. So if you go back over here, maybe someone can help me again. I don't know how to do that, but let's see. We don't have enough colors. Oh, maybe we do. They're hiding. Oh, this is like a child's playground. Okay. Not that many though. So for example, I mean, this is a small network, but maybe you divide the network into 4 quadrants and you want to balance the network load. And if you want to go from here to here, you take the scenic route first. You randomly flip a coin. You go from here to here first, and then from here to here next. The next time you want to communicate between here to here, you flip another coin. Maybe you choose an intermediate destination. You basically, what you do is you choose an intermediate quadrant, and then intermediate and a node in that quadrant. You route to that first, and then from there you route to the destination. So in this first case, you chose this quadrant and this node in that quadrant. In the next case, maybe you choose this node in this quadrant. So you route your XY routing there, and then from here to the destination, you route via XY routing, right? Basically, this way you took different paths from A to X, and you selected those paths randomly based on some randomized algorithm. And the good news is if you're truly random, and if you actually partition your network fine-grained enough, this could lead to a very nice overall network balance, right? And if there's enough nodes communicating, etc., under some conditions, you'll have a very nice network balance. You'll utilize all of your links. That makes sense, hopefully, right? Intuitively. Proofs, read Valiant's paper. Now, of course, this is good for balancing network load, but that may not be your goal. This is bad for latency potentially, right? Because now you're actually routing somewhere else. And this is not always 4 quadrants. Think about 16 quadrants. Maybe you first route over here and then from there to here, right? So this sort of algorithm is not good for your latency. Of course, you could restrict the algorithm. You can say the quadrants that I'm going to route from a given node is restricted to some quadrants that are actually closer to the destination, right? You don't route over here first and then back over here. So it could be a little bit more performance aware. So it's possible to actually change the algorithm, but then you lose some of the properties of balancing the network load across the entire network. You may balance in pieces of the network, but maybe not the entire network. So it's good to think about these things. In the end, your goal is to balance network load, but also hopefully get performance. Okay, we can get back to it. Thanks. Okay, I'll let you do it. So basically, the big upside is balancing network load. If your goal is that, this achieves it nicely. Of course, you need to make it work. I'm going to do that. Okay, thank you. Yeah, the downside is non-minimal. Packet latency can increase, and it actually does increase. Not in every single case, but on average, it increases. And you could do optimizations, of course, right? For example, one optimization is to do this on high load. If you have low load, your network is not very well utilized. Maybe you don't care about how you distribute the load, right? And as I said, you can restrict the intermediate node to be closed, maybe in the same area, vicinity. Quadrant may not be the right word over here. Okay, so basically, that's the idea. This is an example of a non-minimal adaptive algorithm that is oblivious to the network state. It basically doesn't care about the network state. Of course, you could extend it with network state, but then it becomes fully adaptive, let's say. Okay, so these are the papers. If you're interested, you can take a look. So like fully adaptive routing, essentially, or maybe I shouldn't say fully adaptive. I should have used oblivious over here. If you make it adaptive, you actually do. I shouldn't have used adaptive over here. This is oblivious. It's not adapting to the network load. It's basically balancing the network load, but it could be non-minimal. Right? Now, if you want to be adaptive, you need to actually look at the states of the network, either the vicinity of your router or more farther away routers. And we discussed this already. One way of doing that, there are two ways of doing it. One is keeping minimality. You basically have minimal number of hops. And the idea is you always pick which productive output port to send a packet to. Productive output port is the port that gets the packet closer to its destination. I don't know if I want to switch, but if you look at this, for example, if you want to go from A to X, in this particular router, you have two productive output ports, actually. If you don't restrict yourself to XY routing, this is one productive output port, this is one productive output port. Both of them are equidistant to X. Taking one output port doesn't penalize you, doesn't take you far away from X, right? Now, if you're here, you can take this one or this one. Both of them are productive output ports. Not this one. That's not a productive output port because that takes you far away from your destination, right? If you're here, again, this is productive, this is productive. This is not productive, this is not productive because that takes you far away from your destination. So basically, at every single router, you know that there is a productive output port if you know your network topology, and you choose the productive output port. You make a choice based on the set of productive output ports, and the decision is based on which productive output port actually has less contention, for example, downstream at some area. Okay, that's minimal adaptive. Non-minimal adaptive is actually really fully adaptive. Here, you can choose non-productive output ports as well. You basically say, I don't care about productive, non-productive. If there's congestion, I think either local congestion or global congestion, I'm going to escape from it. Meaning, if it takes me farther away from my destination, it's okay. Hopefully, I'll get through to the destination from a less congested route, and this may actually be good for latency also, because you avoid congestion. Okay, so basically, minimal adaptive is aware of local congestion. It could be aware of global congestion also, but the minimality restricts achievable link utilization, load balance. Non-minimal adaptive, it can achieve better network utilization. It exploits path diversity better in the network, and it can actually lead to a better load balance. But now it causes a problem, which we didn't discuss before, which is live lock, right? Because if you make the explicit decision of choosing a non-productive output port, how do you guarantee that you reach your destination eventually? And that's the live lock problem. You could be circling around the network without ever reaching your destination because you always take an unproductive port because you didn't design your network to be not live lock free. Right? That's the problem. And that is usually a problem with fully adaptive, essentially always a problem with fully adaptive algorithms. Okay. But these are important to have, actually. Adaptive routing is really important to have because you can avoid faulty links and routers. And the idea is route around faults. Deterministic routing cannot handle faulty components. Oblivious can, but it needs to be modified to be aware of faults. But if you're adaptive, you can route around faults, basically. You say this area that I'm going to avoid because it's faulty, right? I cannot route through it. To be able to do this, you need to change the routing table to disable faulty routes or faulty possibilities of going through a faulty router. This, of course, assumes that you detect the faulty link and router, right? If you don't know whether something is faulty, you cannot route around it. So there needs to be some detection mechanism to be able to do that. Okay, so this is some work that we have done in this area that actually satisfy a lot of properties like overhead, fully distributed, and guaranteed delivery when you have faults appearing at different parts of the network. This is a tough area, not easy. especially if you want to satisfy all these three different properties. Because with high overhead, you can do anything. With a lot of information, centralized information about everything, you can do a lot of things. But if you want low overhead as well as local information, not global, full information about the network, then what you can do is more limited. Okay. Any questions? So that's routing. We could talk about more routing algorithms, but we don't have time for that. Now let's talk about the third major aspect of network design, which is buffering and flow control. And again, this is also tightly integrated with routing. Because routing algorithms are affected by how you buffer and how you do flow control. So we already discussed circuit and packet switching. I'm not going to discuss that. We already discussed that there are actually different types of networks that exist. We already discussed kind of this one, but just to remind you, you normally have some sort of packet format. If you have packet switch networks, there needs to be some header which has some routing and control information, like the destination, for example. There needs to be some payload, like data. It could be divided into smaller pieces, of course. And there's usually some sort of error code, like a cyclic redundancy check code or MAC code, something like that, so that you make sure that the interconnect errors are tolerated to some level, to some degree, of course. Okay, so assuming that you have some sort of packet switch network, how do you handle contention? Circuit switching, we discussed. Handling contention is not easy because once you contend, you have to set up, you have to tear down the path and set up the path again. In packet switching, the simple question is you have two packets, one coming from the top, one coming from the bottom, and they both want to go to the left output port over here. They're trying to use the same link at the same time. What do you do? What are your choices? Anybody? Packet A, packet B. Yes. Say it again. Deflecting. Okay, you deflect one. What else are your choices? Okay, and what do you do with the other one? Okay, you basically buffer one of them, right? So you buffer one of them, you deflect one of them. What else? Yes. Exactly, yeah. I think these are three fundamental choices unless someone comes up with another one. Actually, there are some smart ways of thinking about it. You could potentially combine them and disaggregate them later, but it may not be possible unless you have nice data patterns. So if they actually are sending the same data, maybe you can compress them together and send them together, right? But we're not going to talk about that. Those are limited choices. More general purpose choices are you can buffer one and send one of them, the prioritized one first, and then the buffered one next in the next cycle. You can drop one and send a message saying to the source, I dropped your packet, resend it. Or you can misroute one, meaning deflect one. You can basically say, you basically prioritize one over the other and send it through the productive output port, and you send the other one on a non-productive output port. And that's called misrouting. Or you could decide based on a variety of solutions. You can employ a combination of these things, of course. So clearly there are trade-offs associated with it. Buffering requires buffers inside the router and also allocation of buffers, the allocation of buffers. We'll see that in a little bit. Dropping requires an ability to tell the sender to retransmit. That requires basically more pressure on the network. You basically send some information on the network, either on the same network or a separate network, saying that I dropped your packet. Misrouting one requires the ability to misroute first, send something to a non-productive output port, but now you need to handle the live-like freedom issue that we discussed, right? So all of these have trade-offs in the end. And we're going to see some of these trade-offs tomorrow. Yes. Yeah, I mean, it's certainly possible. You basically get dropped. You mean dropped, right? You could keep getting dropped, right? Yeah. Yeah, yeah. Yeah, I mean, it's certainly possible. So dropping also has the live lock freedom problem, actually. How do you ensure that you don't keep getting dropped forever? So there needs to be mechanisms to ensure that you don't have live lock. If you have buffering, you don't have deadlock. If you have a combination, you don't have both live lock and deadlock, maybe. So it's good to think about that. Okay, so let's take a look at some of the flow control methods. We already talked about circuit switching. We're going to talk about bufferless, maybe more so tomorrow. And we're going to look at different ways of doing buffered flow control as well. And in the end, it's all trade-offs, basically. And in the end, tomorrow, we're going to see actually a combination of both buffered and bufferless, because purely bufferless and purely buffered are actually two, in my opinion, extreme. Combining them together actually helps things, as we have seen in research. Okay, circuit switching. Essentially, the issue with circuit switching, well, the idea is basically you pre-allocate switches or resources across multiple switches for a given flow. Flow meaning source and destination communicating pair. So in order to do this, you need to send a probe to set up the path for pre-allocation. And the granularity of resource allocation is huge, if you think about it. Basically, you're really allocating resource across the entire path. You're not allocating the entire switch, of course. You're allocating a particular input-output pair in a switch, but that cannot be used. That output node cannot be used by any other communicating source-destination pair. So the huge upside is there's no need for buffering, no contention, because you eliminated it. Nobody can communicate across that path, and the flow's performance is isolated during that communication. And this can handle arbitrary message sizes, because now you can actually pump through data, as we discussed, right? There needs to be, doesn't need to be buffering. You're limited by the frequency of the network and how fast you can actually send the data. And of course, the latency of the interconnect. The downside is you get lower link utilization because two flows cannot use the same link. And you need to have some sort of setup and tear down or handshake overhead to set up and tear down a circuit. Okay, that's circuit switching. Now let's take a look at packet switching. You have packets. One idea is doing bufferless deflection routing, as mentioned. This is actually a very old idea also. All of these ideas are old. This is from 1960s. There's a beautiful technical report by Paul Baran on distributed communication networks. And a lot of the ideas inside this actually went to the internet. And the idea here is you never buffer packets in the network. The router doesn't have any buffers. When two packets contend for the same link, one gets deflected. If two packets can both go on productive output ports, that's fine, no problem, of course. But if one has to go through a non-productive output port because there are not enough productive output ports available and because there's contention, one gets deflected. This is also called hot potato routing. Basically, if you think about hot potato, nobody wants to hold the hot potato. It's too hot. So you basically throw it to someone else, and someone else, that person throws it to someone else, and eventually it gets to its destination, which is the garbage, maybe, I don't know. That's the joke, of course. It's actually hot potato routing, that's the real term. So this is a 3x3 network. Let's see that you have two packets. They both need to go to this destination, and they both contend at this router. One of them gets prioritized. The red one wins the arbitration for the output port, and it gets to its destination in the next cycle. But because we have no buffering, we cannot buffer the blue one. So the blue one gets misrouted to a scenic route, which takes it longer. And eventually the blue one makes its way into the destination because it can take the productive output ports in the other routers, right, in this particular case. So what's happening over here is you're really using the links as temporary buffers, right? Because there's a link that's available and you don't have any buffers, you send it on that link and hope that eventually that thing that you misrouted, the packet you misrouted, gets to its destination, right? So you can think of it as links as buffers. And new traffic can be injected whenever there's a free output link from the injector's perspective. And how do you ensure live lock freedom? That's something we're going to discuss soon, well, tomorrow. The big advantage of this is input buffers. Normally you have, we're going to see this router also a little bit later, but you have input buffers. This is a 4x4 or 5x5 router if you think about the local link also, because there's a local injection port and local ejection port as well. This is your 5x5 router. And normally you have buffering. That's kind of the traditional thinking. And you have a lot of buffers to essentially smooth the load on the network. And you eliminate them basically. Instead of using these buffers, if your router is pipelined, you use the pipeline latches as buffers, and you certainly use the network links as buffers. So you basically replace those buffers with some other logic. And we're going to see this is actually not that easy to build. We thought when we actually wrote one of the first papers, which is over here in on-chip networks, it was easy to build, but it's not easy to build, as we will see. But that leads to a lot of interesting ideas. So basically, these are the major issues in bufferless deflection routing. Live lock. How do you ensure a packet gets to its destination? There's also higher level deadlock issues that we will also cover tomorrow. There's some router complexity to handle the live lock issues. And also a performance and congestion at high loads. One of the good things about buffers is you could keep putting stuff into the buffers, meaning nodes can keep injecting into the network, right? So a network can actually sustain a very high level of load if you have enough buffers in the network. If you don't have buffers, you cannot keep injecting in the network, right? Because you don't have buffers, links are limited. As a result, you have some congestion issues at high loads, meaning if your injection rate is high. So people have looked at how to actually handle this high load problem and to get high performance and also fairness and congestion, better congestion handling at high loads. We may look at that tomorrow. And this is one of the papers in the area, and we've written multiple papers to reduce the complexity. And eventually we settled that you actually need to have some buffers. But it's always good to actually take the, let's say, extreme stand and try to build something that no one is building, let's say. Everybody was building bufferless routers. We said, why not build buffered routers? Why not build some bufferless routers and start from bufferless and see what the spectrum looks like between bufferless and buffered? Okay, and that led us to actually these hierarchical rings with deflection routing, which is nice and implemented in real systems. Okay, so these are some papers on the area that we may cover some of them tomorrow. Okay, these exist in real systems. That's the good part. Okay, let's talk about buffering. Buffering is actually interesting because there's a lot of work on buffering. So if you look at the interconnection networks paper that I mentioned, a lot of it is actually dedicated to buffering and how to handle buffering. And there are multiple ways of doing that. Some of them are not nice, let's say. This one is not nice, for example. It's old, store and forward. This is what people used to do in the past. You have packet-based flow control, but you copy the entire packet into the router before moving to the next router or node. So basically, the flow control unit is at the entire packet. So let's take a look at source and destination. These are the routers. You need to copy the entire packet into the router so that you can move to the next one. Your links may or may not copy the entire packet in one cycle. So you do it in multiple cycles. So this leads to high per packet latency because the entire packet needs to move to one router before it moves to the next router. That's why it's called store the packet and forward. And it also requires high buffering because you need to buffer the entire packet per node, right? So imagine you have many packets from different nodes, then you actually have a problem. So this is not used in many networks. So the question is, can we do better? And the answer is yes, absolutely. So this is another form of packet-based flow control. This is cut through. You start forwarding as soon as the header is received and the resources, buffer and channel are allocated. This leads to a reduction in latency, but not a reduction in terms of storage. You still need to allocate buffers and channel bandwidth for full packets, basically. It looks like this. So basically, your packet can get to the next node earlier because you have your header can go and the middle things can go, but you still need buffering for the entire packet. So if the packets are large, you're in trouble, basically. Okay. So essentially, if the output port is blocked, meaning if the output port, so in this particular case, this output port is blocked, you cannot go here, but you still get things in between. So in the worst case, your buffering needs to be the same as the size of your packets. Right? This is the downside of cut-through flow control. You let the tail continue and the head is blocked, absorbing the whole message into the switch. And this requires you to have a buffer large enough to hold the largest packet. So you degenerate into store and forward. Does that make sense? So you need to store the entire packet in the end. Your latency may be lower if the blocking is, if you don't have a lot of congestion. So this saves some latency, but it doesn't solve the buffering problem. Yeah, basically it degenerates to store and forward with high contention in the end. Even the latency benefits are not there if you have high contention. Okay, so the question is, can we do better again? And this is how normally buffered flow control is done in many on-chip networks and also many off-chip networks like Cray 3D, for example. You break the packets into smaller, usually smaller flits. Flit is the buffer and bandwidth allocation unit, buffer and channel allocation unit. So buffers are not dedicated to whole packets, but they're dedicated to much smaller pieces of it, packets, flits, essentially. Flit means flow control unit. And you break it down into header, body, and tail flits. And flits are sent across the fabric, meaning the interconnect, in a wormhole fashion. It's like a worm. The tail follows the body follows the earlier body, and earlier body follows the head. That's like a worm, right? That's why it's called wormhole. Body follows head, tail follows body. And it's pipelined. You don't need the entire packet in a given router. Pieces of the packet are in different routers, but they're in a pipeline fashion. They follow each other. So if the head is blocked, the rest of the packet stops. The routing information is only in the header, only in the head flit. So for example, if your packet is 512 bytes, and if your channel is 8 bytes, you can have 64 flits, right? 64 flits forming a single packet. But your storage inside the buffers may be 4 or 5 flits, right? Whatever. We're going to talk about that also. It's not that easy actually to make it 4 or 5, but it could be small. So the question is, of course, how does the body and tail know where to go? The nice thing over here is the header needs to go first. It's essentially leaves some breadcrumbs, meaning it changes the switch to say that I'm the header packet and treat the remaining flits that are coming from this, let's say, channel as my followers and send them to the same direction. That's the idea, basically. Follow the head. This requires some state in the router. But this also simplifies the process because the body and tail flits don't need to have any headers, right? Because the header actually sets the router. Okay, in this case, one of the nice things about wormhole flow control, in addition to reducing the buffering requirements, because now your buffers are independent of the packet size, right? You can size your buffers independently of your packet size. You need to still be careful for the reasons that we're going to discuss. But also your latency is almost independent of the distance for long messages. Because now you're actually going through the network. If your message is very long, let's say 64 flits, then you basically are pipelining things. Right? So it's good to think about this. Okay, so wormhole flow control is used because it has serious advantages over store and forward. It's lower latency, it has more efficient buffer utilization. The limitations is it suffers from still congestion, meaning head of line blocking. I'm going to define this. Basically, if head flit cannot move due to contention, another worm cannot proceed even though links may be idle. And this is fundamentally because of in-order scheduling of worms. If you have out-of-order scheduling, then you can actually fix this if you've seen out-of-order execution, but people have not moved to out-of-order execution in router design as much. Okay, so let's take a look at this example. So these are your input queues. This is your switching fabric. These are your output channels. Clearly, the input queues are FIFO. That's the assumption. And this one wants to take output 1. This one also wants to take output 1. And this one goes to output 1. Unfortunately, even though there's something that can go to output 2 over here, it cannot because this one is blocked. This is called head of line blocking. And the main reason is, and these are completely different flows. One of the flows wants to go to output 1. The other flow over here happens to go to output 1 also, needs to go to output 1. This one wins, this one loses, but because the router cannot examine the other heads of the worms, it's stuck. And the fundamental issue is really in-order scheduling, FIFO routers. And one solution could be to examine all possible heads of worms that are inside all of the possible queues And then you will discover that this actually wants to go to 2, and it should not be blocked, and you'll send it. Now, that increases the complexity of the router. It's kind of like out-of-order execution processors, right? So people didn't want to do that. So their solution was to do something else, as we will see, which is virtual channels. This is where the terminology gets a bit crazy, I think. But anyway, it's a well-established terminology. Once you understand that, it becomes interesting. So a worm can be before another in the router input buffer. And due to the FIFO nature, the second worm cannot be scheduled, even though it may need to access another output port that is free. And that's I explained already. So let's take a look at this pictorially. So you have this blue packet, and it needs to go to this blue destination. Currently, the blue destination is blocked by other packets, and this red packet needs to go to the red destination. Let's see what happens. So the buffer here is full. Blue cannot proceed over here. We're doing wormhole routing. So blue is occupying things over here. What happens is, here the channel is idle, but the red packet is blocked behind the blue packet. Okay, that can happen, clearly. What is the solution, as we will see? So red holds this channel, and this channel remains idle until the red proceeds. This should be red over here, not wheat. Okay, so the idea is basically, in the seminal paper, Bill Daly introduced virtual channel flow control. Essentially, the idea is multiplex multiple channels over one physical channel. Instead of doing complete out-of-order execution, divide a single queue into multiple queues, such that you can look at the heads of those queues separately, and you can do some level of scheduling across them, right? Because a single FIFO queue is not enough, right? You cannot look at what's next, have multiple FIFO queues, and allocate them nicely to different worms, such that you can do scheduling across those different queues. So basically, you divide up the input buffer into multiple buffers sharing a single physical channel. It looks like this, basically. Instead of having a single queue, you have multiple queues. And if the red packet is here, the blue packet can be here, and you can arbitrate across them now. You don't do full out-of-order scheduling. Principles like this have been applied to out-of-order processors also. Instead of doing completely out-of-order execution, you have multiple FIFO queues, and you schedule from the heads of the multiple FIFO queues. So it's very similar principles to instruction scheduling, actually. Okay, this is a nice paper. You can take a look at it. And this is essentially what it does. Instead of having, for example, assuming equal area FIFO buffer, equal area buffering, instead of having a 16-flit FIFO queue, have four flit FIFO queues, right? And each of them can house worms that could be arbitrated independently. Now, your arbiter is slightly more complex because you have more things to consider, but it's not as complex as looking at everything in the 16 queue, right? That's the idea. Okay, so this is the benefit that you get. Assume that you have 2 virtual channels right now. This is still blocked. The blue packet cannot go its destination. But now, because there is a virtual channel, blue packet cannot proceed, but red packet can go to another FIFO queue and can reach its destination. So the blue packet did not prevent red packet from reaching its destination because they didn't share a single FIFO queue. That's the idea. If you know out-of-order scheduling, this is a very simple idea. If you don't know out-of-order scheduling, take some time to think. Okay. So this is the modern virtual channel-based router, basically, the complexity that we wanted to avoid when we started looking at bufferless routing, but we're going to talk about that. It's actually quite complex. You need to decide which virtual channel to allocate your worm into. And then there's some routing logic to decide which output channel each input channel gets mapped to. And then there's some virtual channel allocation in the downstream router. So you need to do the virtual channel allocation in the downstream router. And that requires some things that are coming in over here, credits, which we will see. You need to do some sort of flow control. You need to allocate the switch. Once you actually decide what to schedule through the switch, you need to do this switch allocation. So actually, modern routers are quite complicated. This doesn't even do justice to it. Okay, there are other uses of virtual channels. One use is actually deadlock avoidance. So if you have multiple virtual channels, multiple FIFO queues, you enforce switching to a different set of virtual channels such that on some terms, so that you can break the cyclic dependency of resources. This is one idea that people have used. You can enforce some order on the virtual channels. You can have escape virtual channels, have at least one virtual channel, meaning a FIFO queue, that uses deadlock-free routing. The other ones may not use deadlock-free routing. So you can actually play a lot of tricks if you have a lot of buffering in your system or queuing in your system. There's another type of deadlock, which is protocol level deadlock. For example, you have address packets or control packets and data packets. And if they use the same network, a control packet may delay a data packet, or a data packet may actually cause starvation to a control packet. But one way to avoid this actually to ensure to partition the network with, such that these use different virtual channels. If they actually use different virtual channels, you prevent cycles due to intermixing of different packet classes. This will become more clear perhaps when we talk about one type of protocol level deadlock tomorrow. But there are a lot of issues basically to think about when you design a network. It's not that easy. And then if you have virtual channels, you can actually assign them different priorities. Some virtual channels may have higher priority than others. And this can enable you to prioritize different traffic classes. Okay, so this is a review of buffered flow control. We had store and forward, which was a bad idea because latency was high, buffering was high. We shrink the buffers, reduce the latency. We did cut through, wormhole. Wormhole is much better than cut through. So maybe we should remove cut through from there. And then we figured out there's still head of line blocking because we have a single FIFO queue for a given input port or input channel. And that led to weird issues like this, even though you have the blue cannot proceed and the blue packet prevents a red packet from not proceeding, even though the channel is idle. Basically, we're not even utilizing the links nicely because we have a single FIFO queue. And we broke that by actually dividing the FIFO queue into multiple FIFO queues that are potentially each smaller. But at least now you can schedule across those FIFO queues. Okay, so that's kind of a very short summary. You can see that there's a lot of headaches in buffering. Okay, let me give you a few more headaches and then we're going to stop and then we're going to start tomorrow. Essentially, headaches don't end if you have buffers like this. Communicating buffer availability is something that we have not thought about, maybe you have not considered, right? So you need to communicate before you send a packet to a downstream router, to the next router, you need to know whether a buffer is available, right? Because you send the packet and the buffer is not available, what do? The router should drop the packet, right? Because the buffer is not available. But then you're back to dropping, not buffering, right? So if you want to have a purely buffered system and you don't want any dropping, you don't want any misrouting, you need to communicate whether or not a buffer is available before the previous router makes a decision of sending a packet to you. And this requires some delay, clearly. If the routers make decisions at different points, you need to actually provision your routers, or provision your buffers such that the previous router doesn't make a wrong decision, meaning send you a packet even though you don't, or send you a flit even though you don't have a buffer. So this actually causes not only communication issues, but also latency issues. And also it increases the buffer sizes because you cannot have a single buffer and manage it so efficiently because there's communication delay in terms of communicating the buffer availability. So there are three major ways of actually communicating buffer availability. One is credit-based, on-off, ACK-NACK. Let's cover at least one. Credit-based flow control says upstream router knows how many buffers are available downstream. Downstream is where you're sending. It's like a river, right? Downstream is you're sending things, although people abuse that terminology also. So downstream is where you're sending the packet. And downstream informs the upstream router by passing back credits to upstream, meaning how many buffers are available. This requires significant upstream signaling. So there's an overhead of signaling. You need to have a back network that tells you. This is called a credit network usually. And that credit network needs to tell you how many buffers are available. On-off means downstream has an on-off signal to upstream saying, I'm on, meaning you could keep sending. At some point, it says, I'm off, stop sending to me, right? These are different trade-offs. ACK-NACK says upstream optimistically sends downstream. Buffer cannot be deallocated until ACK or NACK is received. So basically, there's some dropping, but you cannot deallocate the buffer in the upstream router until you receive an ACK from the downstream router. So you send the packet optimistically. If you receive an ACK, you try again. So it's a smaller dropping mechanism. You don't drop in the entire network, you drop locally. Yes. Yes. Yeah. Mm-hmm. Mm-hmm. Yeah. I mean, I like the idea, but that goes against pure buffered networks. So now you're combining buffering and deflection. And I agree, that's one way of actually solving the issue. Because whenever you have deflection, you don't need to communicate buffer availability as much, let's say. Yeah. Yeah. And that's what we're going to talk about tomorrow, basically. Yeah. That's very good, though. Yeah. Okay, let's take a look at credit-based flow control very quickly. I'll start from here tomorrow. But essentially, this is node 1 and node 2. Node 1, at some point, node 2, node 1 is going to send something to node 2. At some point, node 2 sends a flit to the next router. We don't care about the next router right now. It basically sends a credit to node 1. This arrives at T2. And this credit needs some processing time. And at some point, node 1 says, oh, I have some credit, so I can send it to send my flit to node 2. And it sends a credit back to the previous router. You can see that credits are flowing. You could actually make it coarser grained, but coarser grained requires more buffering. And then the split is processed, and then eventually you do this. This is called the credit round trip delay. Whenever the, okay, I'll read it. This is the time between when the buffer empties in node 2 and when the next flit can be processed from the same buffer entry. And this really determines your throughput in the network. And this is, you need to know this delay so that you can size your buffers such that you can tolerate this credit round trip delay. If you don't tolerate this credit round trip delay, you're not utilizing your network very well. As a result, you get significant throughput degradation. Even though your topology may be able to support very high throughput, you just don't have enough buffers in the network because you need to communicate buffer availability across different nodes. This may require some time to really understand, so I'll let you think about it. Okay, I'm not going to go through on-off right now. I'll let you study on-off, maybe yourself, but they all have similar issues. And tomorrow, I think we can start with on-off a little bit, and then maybe we'll start with interconnection network performance. Does that sound good? Okay, cool. I guess I'll see you tomorrow.